This video contains the solutions for numbers 18 through 21, your practice AP physics test. Numbers 18 and 19 refer to this situation here. I've done some scribbling there already. Maybe we should redraw that so we can do it again. Got a table, pulley, mass 1 going over the pulley, and mass 2. And information here says a block of mass M1 on a horizontal table connected to a hanging block of mass M2 by a string that passes over a pulley as above. The acceleration of the blocks is 0.6 g. Assume that friction and the mass of the string are negligible. And since they didn't say anything about it, we're also assuming that this has no moment of inertia that's going to make any difference. They would have to tell us about it if it did. It would make it a much harder problem. And it's tricky enough as it is. So no moment of inertia here. Why not? How do we know? Because they didn't say anything about it. So don't second guess yourself there. What are the forces acting on these blocks? Well, let's see. The tension here and the tension of the string here. And in this case, these two are equal. Because why? I'm going to pause the video for 1 second and think about that. Or under what circumstances would they not be equal? Well, they would not be equal if this did actually have some, if we were taking into account its moment of inertia. Then we could not count on those two being equal to each other. But here, since we're ignoring the pulley, it's basically like it isn't there. So they have to have the same tension. And then here, gravity is acting on this one. That would be M2G. And there's a normal force and a gravitational force here, but those balance out. There's no friction, right? So this is actually the only force that's contributing to the acceleration of that block. So they want to know, what is the tension in the string? Well, let's write down, let's set up Newton's second law for both blocks and see where that gets us. The net force on this is T. So force equals, mass times acceleration, which is 0.6 g. But that's not a choice. All of the answer choices are in terms of M2. So I think I'm going to have to do something with this one too. Net force on this one, it is accelerating downward, so this force is bigger than this. So M2g minus T, that's force, net force, equals mass M2 times acceleration. And this actually looks like an equation where I can solve for T in terms of M2 and G. That's what the answers look like. So let's do that. Move the T to the other side. That gives me T is equal to M2G minus M2 times 0.6 G. And let's see, here I have a G minus 0.6 of a G, right? If I factor the M, let me do that actually, so you can see that. If you factor out the M2, so that's like a whole G minus 0.6 of a G, and that leaves 0.4 of a G, and 0.4 G times M2 is answer choice B. So this is number 16. Oops, sorry, 18. And number 19, we have, they want to know the ratio of the masses. Well, that should be pretty easy to do because I have them both in terms of T, right? I just solved T equals this, and I already have that, so let's set those equal to each other. Since this equals T and this equals T, then M1 times 0.6 G must be equal to M2 times 0.4 G. So the G's cancel out, and what do they want? They wanted the ratio. They want M2 to M1. So I'm going to divide the M1 over here and divide the 0.4 over here. So that would be equal to 0.6 over 0.4, or 6 over 4, or 3 to 2. and 3 over 2 is equal to 1.5. That's correct. Answer choice is D. Numbers 20 and 21 refer to another diagram where we have a block connected to a spring. This is block 1 over a pulley in block 2. And I think there is friction this time, so let's see what they say. In the system of 2 blocks and a spring shown above, blocks 1 and 2 are connected by a string that passes over a pulley. The initially unstretched spring, so it starts at its relaxed length, connects block 1 to a rigid wall. The wall's not moving. That's good, because walls aren't supposed to move. Block 1 is released from rest, initially slides to the right, and is eventually brought to rest by the spring and friction on the horizontal surface. So maybe you can imagine there's a couple ways this could go depending on the spring. It could kind of oscillate a little bit and then eventually end up with block 2 pulling on it. Friction stopped it from doing, bouncing back and forth, right? Friction will eventually take away all of the energy. Normally, a system like that, if there were no friction, would keep oscillating with a constant mechanical energy, like the kinetic energy and potential energy would add up to some constant. But here, energy is being tapped off the system by friction, so it'll eventually stop. Where does it stop exactly? Well, it depends on the details, which they haven't given us, so let's see what they ask. Which of the following is true of the energy of the system during the process? Well, we kind of talked about that. It's not conserved because there's friction present. If there's friction present, energy is not conserved, period. The total mechanical energy of the system increases. Well, there'd have to be something doing work on the system, adding energy in, and friction's doing work, but it's taking energy out. So if it eventually stops, if everything stops, that means there's no kinetic energy. There would be a little bit of potential depending on where that stopped, but it would certainly be less than what we had at the start. The energy lost to friction is equal to the gain in the potential energy of the spring. Okay, let's go through that. The energy lost to friction, right, how much energy we lost, is equal to the gain in the potential energy of the spring. Well, that kind of sounds like energy being conserved, right? If this energy that was lost or gained here, that's how energy gets conserved, right? It goes from potential to kinetic or vice versa. So that doesn't sound good, right? I think friction is going to just dissipate energy and it's not going to be stored up anywhere. Answer choice D, the potential energy lost by block 2. So this eventually drops some, right? That potential energy lost is less in magnitude than the potential energy gained by the spring. So let's think about that. The total energy of the system, up here we've got the spring and friction tapping off some of the energy. And here we have this much potential energy, right? So everything, the total energy, like including what we lost to friction, has to be conserved. So I think that what we would have is the potential energy up here of the spring plus whatever we lost to friction. Let's just call that lost friction for lack of a variable there. And that's got to be equal to the change in gravitational potential energy here. Sorry, I should use U's here. CP physics. I should be using U. So which one is bigger? I think that's what we're down to here. The potential energy lost by the block is less than the magnitude. No, it looks like it's more, right? This one is that one plus the friction. So I think E says the potential energy lost by block 2 is greater in magnitude than the potential energy gained by the spring. That's true, right? Because some of the energy up here in this part of the system was lost to friction. So the amount that this dropped, that change in energy is going to be bigger than what the spring gained because of the loss to friction. So the correct answer choice is E. And number 21, after block 1 comes to rest, the force exerted on it by the spring must be equal in magnitude to, well, it would be in static equilibrium at that point. So let's see what the forces are. We want to know, after block 1 comes to rest, the force exerted on it by the spring. Okay, so here's block 1 at the end. We've got the spring force acting on it in this direction, right? It's pulling it back toward equilibrium. And on the other direction, we have the tension of the string. And if it would otherwise move this way, then the frictional force, in this case the static frictional force, is going to be, force of friction is going to be this way, right? Because if that wasn't there, the block would be pulled by the spring back. So the static frictional force is in the other direction, right? Of course, if friction wasn't there at all, it would just oscillate. So there must be some friction if it's in equilibrium. And that looks like, so this has to be balanced with those two. That would have to equal that if the net force is 0. So 0, no, it's not just the frictional force, it's the sum of those two, the vector sum of the forces on block 1 due to friction and tension in the string. So it's the sum of those two.